This is part 2 of the video notes for Goal 1B, graphing functions. For our first example, we're going to be practicing vertical shifts on a quadratic parent function. And you'll notice in your packet that the critical values of a parent quadratic function are clearly labeled as 0, 0, 1, 1, 2, 4, and then the same points on the other side of the x-axis at negative 1, 1 and negative 2, 4. Quadratic functions should always be symmetrical through their vertex. When you graph a quadratic function, I will be looking that the graph is symmetrical through its vertical axis. I'll also be checking the width, because the width of a quadratic function is determined by its scale factor or by its coefficient. So when you're drawing a function that does not have a coefficient, you want this relationship of 1, 1 and 2, 4 to keep your quadratic fairly narrow. The first of the translations that we're going to do are that marker's dead. The first of the translations that we're going to do is y equals x squared plus 3. And so when you have a function like this, you can type it into your graphing calculator and get an idea of how the shift is going to move, or you can do an analysis of the equation. This plus 3 is being applied to the output of the function. And I can tell this because the input of the function is x, and the plus 3 has not been grouped with the x. Well, output is y, and if you add 3 to the output of a function, you're basically increasing the y values by 3. So I have a y value here at 4, go up 1, 2, 3. I have a y value here at 1, go up 1, 2, 3. And I have one at 0, and another one at 1, and another one at 4. And what you see from a plus 3 is that the function moves up 3 units and maintains its similar shape. The next example is y equals x squared minus 1. This also is being applied to the output of the function because it's not been grouped with the x. And so this is asking us to subtract 1 from each of our y values. 4 minus 1 is 3. 1 minus 1 is 0. 0 minus 1 is negative 1. We'll repeat this on both sides. So what this ends up doing to our quadratic function is lowering it 1 unit. If a real number k, these would be k, is added and subtracted from the output of a function, the graph of the new function will be shifted vertically up or down that number of units. And this is what you need to know about vertical shifts. Example 2 is dedicated to horizontal shifts and focuses on a different one of your parent functions, although these shifts can apply to any function. This graph has also had a few points labeled. We have 0, 0, 1, 1, and 8, 2. Negative 1, negative 1, and negative 8, negative 2. Make sure you apply some curvature at the origin, because that is one of the key features of a cube root or a cubic. And so here is our original graph. We're going to practice horizontal shifting on this graph. The first example we would like to do is f of x equals the cube root of x minus 3. In this case, the minus 3 has been grouped with the x because it is underneath the cube root with the x. This is how you can distinguish an input transformation from an output transformation. You might not see parentheses, but you will have some sort of grouping symbol putting those values together. When we do a function like this, instead of thinking what this is, we actually have to negate it. For example, if we wanted to graph a point at 0, we wouldn't plug in 0 to the function, and we wouldn't plug in -3 to the function. We would plug in 3. And sometimes making a table is a helpful way to understand how a horizontal shift works. Let's look at the outputs we originally had in the function. We had an output at -2, -1, 0, 1, and 2. So we want to achieve those same outputs and see how the function shifts. So let's start with -2. To get an output of -2, we had to have an input of -8 originally. But now, since we're already minusing 3, we no longer need an input of -8. What kind of input do we need? Working backwards, you can see to figure out the necessary input, you have to add 3. If you input -5, -5 minus 3 is -8, and the cube root of -8 is -2. Similarly, if you want an output of -1, you're going to have to add 3 to the usual input to find an input that works. Add 3, add 3, add 3. In order to balance an input transformation, you have to do the opposite operation. So this kind of transformation, instead of moving your function left 3, like the negative might suggest, you move your function to the right 3 units, since you need a number that's 3 units bigger to fight the 3 being subtracted. 1, 2, 3, 1, 2, 3, 1, 2, 3. Same thing on the other side. And what's really important is that we're getting the shape very similar. There is our shifted to the right function. The next example is also an input transformation. We have f of x equals the cube root of x plus 1. And again, if I'm adding 1 to every input value, I'm going to have to put in numbers that are 1 less so that I can add 1 to them. That means that this transformation takes the function left 1 unit. For example 3, we're going to be combining horizontal and vertical shifts. So when shifting a function horizontally and vertically, the order of the transformations does not matter. You can go left, then up, down, then right. What order you do the transformations won't change the outcome of your graph. So we're going to take a look at f of x equals the absolute value of x plus 2 and then minus 3. Again, even without parentheses, I can see that the 2 is with the input. It's been grouped with the absolute value symbols, and that the 3 is with the output. The 3 being with the output means that I'm going to be moving this graph down 3. The plus 2 being with the input means that I'm going to be moving the graph left 2. Again, we need to offset the 2 being added to our input values, so that means we have to put in numbers that are 2 less than what we normally would put in. Let's take this function left 2 and down 3. You'll notice with an absolute value, there aren't very many points that have been labeled with a dot, and that's because an absolute value has a slope of 1, which means every point on the grid is a point that you could use. You'll know that you have constructed your absolute value with the same shape because the legs should technically be parallel since they should have the same slope. The second transformation for example 3 is f of x equals the absolute value of x minus 1 plus 1. Similarly, this input is going to be taking us right 1. This output is going to be taking us up 1. From the original parent, let's go right 1 and up 1. And with this one, the shift is interesting because having a slope of 1 means that these two legs stay the same. Example 4, we're going to focus on vertical stretch and compress. Vertical stretch and compress is considered one of the more challenging transformations that you need to be familiar with, which is why the vertical stretch and compress doesn't come into the rubric until proficient. So you can get a 6 out of 10 without being able to accurately vertically stretch or compress your function. Vertical compression will affect the output, not the input. So all of our x values are going to stay the same. And what we're going to see is that our function is visibly going to stretch out or shrink towards the origin. Our parent function for this example is the cubic function. 2, 1, 2, 3, 4, 5, 6, 7, 8, which has points at 2, 8, and -2, -8. And the two examples that we want to practice with are y equals 3x cubed and y equals 1/2 x cubed. And so we're going to see one vertical stretch and one vertical compression. How you do your scratch work to achieve this compression is up to you. Once you have the points graphed, if you can see that this is 0, 1, and you can multiply that 1 by 3 and graph the new point 0, 3, you have accomplished a stretch without creating a table. Similarly, this point is at 2, 8. And if you multiply the 8 by 3, you find that it's going to go to 2, 24, which basically means it's just a lot higher. And we'll go off the graph quicker. On the flip side, we're going to be doing the same exact transformation. This function is fully symmetric, so it just needs to look the same on both sides. That is a vertical stretch of 3 without creating a table of values to find my ordered pairs. However, you can table your values. Draw a small table to the side. Again, 8 went off the graph, so I'm just going to make a table of the 3 points. And then you can multiply these y values by 3 to find the new ordered pairs. Just be sure that you are only multiplying the y coordinate of each ordered pair. We do not want to multiply the x coordinate of the ordered pairs. Let's try this again, but with 1/2. And this time I'll do the complete table rather than doing my scratch work directly on the graph. I'm going to go ahead and erase this one to give myself just a little bit more space to work with. So we have y equals 1/2 x cubed. And the critical points on a cube graph are the perfect cubes. -2, -8, -1, 1, 0, 0, 1, 1, and 2, 8. Well, the 1/2 out in front means that I need to take all of my y values and multiply them by 1/2. So let's find 1/2 of each output. In this case, instead of using a fraction, I'm going to go ahead and use 0.5 because it's easier for me to graph a decimal, this should be negative, than it is for me to graph a fraction, although 1/2 is easy either way. When we regraph this, we are going to be using x, y, x, y, and we're going to ignore that original column that we used to find our Now we just need to graph these ordered pairs. -2, -4, -1, 1/2, 0, 0, 1, 1/2, and 2, +4. And a 1/2, unfortunately, isn't a dramatic compression, but your function should be wider than it was before. More curvy, larger sit at the center. These are vertical stretches and compressions. Remember, this transformation will only ever affect your output variable, y. The last one is a reflection, although a reflection can be done in tandem with a stretch or compress, because if there was a negative in front with this 1/2, I would be multiplying everything by -1/2, and the reflection would automatically happen. But let's take a look at when only a negative is in front. There's no scale factor as well. For this example, we're going to be focusing on our square root parent function. So just recall those values from earlier in the notes. When the output of the function is multiplied by a factor of -1, the new function is a reflection about the x-axis. So our first example, the negative is on the outside of the function. That means this is going to be an x-axis reflection. Our second example, the negative is on the inside of the function, which tells us that it's going to be a y-axis reflection. You will need to understand both types of reflections to be successful on the rubric. An x-axis reflection means that all of the y values get multiplied by -1. Or essentially, all of the y values will change sign. So 0, 0 stays the same, 1, 1 becomes 1, -1, and 4, 2 becomes 4, -2. Output means y, so if the negative is on the output, you need -y. In the second one, this negative is in the input, which tells me that I'm multiplying my x's by a negative, or that I'm changing my x's sign. So the original point 0, 0 again won't change, but 1, 1 will become -1, 1, and 4, 2 will become -4, 2, because the input value has to change signs. And that is how you do a reflection. Let's try one example together. So this is going to be the last example in our notes, where we do a little bit of all of the transformations, which is essentially how you reach a 10, highly proficient on your rubric. Any parent function, any type of transformation, no errors. This last example is based on the square root parent function because there is a square root. So I'm going to draw the square root parent back on my graph. And then I need to analyze each of the transformations present. The first thing I notice is that it says 1 minus x instead of saying x minus 1. That means that there's going to be multiple transformations in this problem. I highly recommend rewriting this so that it says y equals -x plus 1, which is mathematically equivalent to 1 minus x. I can see now there is a horizontal, not horizontal, there is a, horizontal reflection. There is a horizontal shift, and there is a vertical shift. Which of these operations needs to be completed first? Well, we want to follow the order of operations when we're graphing. So the first thing we want to do is horizontally reflect our picture. Like so. Once we have the reflection complete, we're free to move our points left and up. We don't want to reflect it after we've shifted because the reflection needs to be based on the y-axis. And when you shift the function, you're no longer reflecting across the y-axis by just changing the x values. Take each point, move it left 1 and up 2, left 1 and up 2, and then 0, 0 needs to go, or 1, 1 needs to go left 1 and up 2. I skipped that one. Be careful that you don't draw too much function. The square root has an endpoint and a continuous side. This is the conclusion of part 2 of the video notes for Goal 1B. As a reminder, to be highly proficient, you can graph the families of functions with any transformations, including horizontal, vertical shifts, scale factor, which is our stretch and compress, and flips, which are these reflections. You should be familiar with these transformations without needing the aid of your calculator, but you will be allowed to use your calculator in case you need to check your solutions. If you have a graphing calculator, continue to bring it to class.